Hi everyone, this is Miss Fung. I hope this video finds you well, perhaps extra comfortable, and hopefully very healthy. We are today talking about trig functions of general angles. So not necessarily tied to right triangles at this point, which is counter to what we were talking about perhaps at the start of this chapter where we said trig is all about right triangles. Well, now we're applying trig to all angles. So we're going to be using something called reference angles. We'll define that very shortly here. If you are following along and wanting to take notes, then I recommend having out for you, that was my cat, a notebook or some other means for taking notes, like a piece of paper, your computer, whatever works best for you, a pencil, perhaps some additional colorful utensils. A straight edge would be helpful, and we will get started. But yes, if you hadn't heard those little meows, my cats are around, so I'm hoping they don't get too distracting. Okay, let's dive in. Let's define first a reference angle. All right, a reference angle is, first of all, going to always be an acute angle. So it's going to be formed by the terminal side of theta and our x-axis. So, okay, let's dive into that just a little bit. Acute means certainly less than 90 degrees as opposed to a right angle, which is equal to 90 degrees. And obtuse would be larger than 90 degrees. So we're talking about smaller than 90 degrees. And then the angle is formed by the terminal side of our angle theta. So remember that our terminal side, or really when we're talking about angles in standard position, we always have an initial side right along that x-axis, and then a terminal side that basically shows where the angle ends. So you can see here are all of our terminal sides of our angles. Might be helpful if I use kind of like a highlighter there. Let's see. Terminal sides are all here. There we go. That's a little bit better. So the terminal sides, and then basically wherever the closest way to get to that x-axis, that's how we're going to figure out our reference angle. So you can see in all of these different diagrams that we have the reference angle indicated as this little theta with like a little apostrophe. It might be kind of hard to see. That is how we'll usually show our reference angles in drawings, and we can talk about a reference angle algebraically that way as well. This reads theta prime, so the little theta symbol and then an apostrophe is read as theta prime. So like I said, they're all acute no matter which quadrant of the graph you're in. And you also might notice from our diagrams that the angles don't have an arrow. They don't have a directional indicating, which way around the axis they go, unlike other angles that are plotted in standard position. That's because they are always going to be positive, so we don't need a directional, and they're always acute. So again, and we don't need a directional there. Just a really quick reminder that when we're talking about these quadrants, if I were to have my x and y axis, I've got 4 different quadrants here formed by the x and y axis. So quadrant 1 is up here, quadrant 2 is over here, quadrant 3 down there, and quadrant 4 down here. And they're, for whatever reason, almost always indicated with Roman numerals, so you'll see that. Now, the kind of formulas that are written down here for how we determine the measure of our reference angles, I just want to go through those kind of quickly here. They might, want to pause and actually add those specifically to your notes. But when I actually determine my reference angles, I don't find myself often using these formulas. And most of my students know that I don't like to try to memorize formulas. It doesn't work very well for my brain. I like to try to make sense of what's happening. So I'll sort of try to do both as we go through this. So in quadrant 1, we can see here that if we've got, ooh, that's not good, let's use yellow. If we have some angle, again, theta, that's plotted in standard position, the reference angle is literally just exactly equal to our angle theta. The acute angle formed by the terminal side of our angle theta and the x-axis, well, that's just the exact same angle. So there's no difference there. In quadrant 2, we could think about it, you know, we've got radians down here and degrees here. So we can think about subtracting our angle theta, our given angle, from either 180 degrees or from pi radians. And that comes from knowing that this whole axis, in fact, if I were to just have a terminal side of my angle right there, then this angle would actually be equal to, in degrees, 180, or in radians, pi. So we're kind of figuring out like how many more either degrees or radians would I need to keep going to complete that, that straight line, essentially. Okay, now in quadrant 3, the formulas look like our angle theta minus 180 or minus pi radians. And then over in quadrant 4, we have now 360 minus theta or 2 pi minus theta. So a full circle minus our given angle. Okay, so again, I will try to explain sort of where these come from, but you can always go back and sort of look at those formulas. Okay, let's give this some practice. So examples we'll see, or problems we'll see utilizing this are, we'll be asked to sketch angles and then find its reference angle. So we're asked to sketch 330 degrees. As you may be getting more familiar with, we are asked to always start with an initial side. So there's my initial side of my angle. And then if it's a positive degree measure or positive radian measure as well, our directional is always going to go counterclockwise. So it's always going to go this way for something that's positive like we're given. So I'm going to save that final directional for once I actually have my terminal side. So I always find it helpful to kind of indicate where these 4 axes are for my angle measures. What I mean is right here, if I were to say have my terminal side right on top of my initial side, that could just be the angle of 0 degrees, which isn't much of an angle at all, but it could also be a full circle or 360 degrees. So that there's a couple possibilities there. Okay, we might have to resketch the initial side, that's all right. Whereas if I were to go just like straight up here, if that was my terminal side, that would be equal to 90 degrees or coterminal with 90 degrees, to recycle some vocab there. If my terminal side was here, or was, is along the axis there, then it would be 180 degrees or coterminal with 180. And then down here, this would be 270 degrees. Okay, so that gives us kind of an idea of where my specific angle of 330 should actually be. So let's put that initial side back. You might want to use an actual straight edge for this. Mine is not going to be super perfect. So let's think about this. 330, well, that's more than 270 degrees, but less than 360. In fact, it's 30 degrees less than 360. But it's, let's see, 60 degrees more than 270. So it's not exactly like halfway. It's maybe a little bit closer to 360 than it is to 270. I don't need to take out a protractor and be super precise about this. We're sketching this angle. So I'm just going to do my best. I'm going to make this, you know, more in the realm of 360 degrees, a little bit further away from 270. But again, not super precise. Okay, so there's my terminal side. Let's get my directional, and we'll label that 330 degrees. So there's my sketched angle. My reference angle, theta prime, I'll label it for now, is here. It's formed by that terminal side and then all the way back up to the x-axis. Never this way though, not this direction. Notice that angle would be very obtuse, much larger than 90 degrees, as opposed to the acute angle. Remember, reference angles will always be acute. So if we're trying to figure out how many degrees that is, and I think I mentioned this a little bit already, I personally tried to ask myself, okay, if this is 330 degrees, how many more degrees is it to get all the way back up to my x-axis that's represented by 360 degrees? So mathematically, you might write that as like, what is 330? Like, what do I have to add to 330? Let's label it theta prime to get to 360 degrees. So of course, to solve this, that's going to look like, okay, theta prime is equal to 360 minus 330. And that actually fills in the formula idea that we looked at on the last slide. Our answer in this case, theta prime, is going to be equal to 30 degrees. Okay, let's look at another example. This time, let's use radians. So we've got radians here. We're supposed to sketch negative 5 pi over 6 radians and then find the reference angle. Okay, so it's very similar as to before. I want to label my various axes with what they represent in radians. I'm going to do that a little bit differently than before because notice this is negative 5 pi over 6. So of course, if my terminal side is here, let's make that bigger, that would still be 0 radians, or I guess even negative 0 radians. That doesn't make much sense, but you know what I mean. Or if I go all the way around a circle, again it's clockwise because we're sketching a negative angle measure, all the way back around would be negative 2 pi. Now we might still be getting used to that because we just introduced this kind of stuff yesterday or maybe over the weekend. But negative 2 pi radians is the full circle just going backwards. So it's a full circle but going clockwise instead of counterclockwise. You can always determine that. Again, if we know 360 is a full circle, we could say, we could use kind of our proportional reasoning as we talked about in yesterday's notes. Okay, so again, we're looking at going this way. So if we were to get to a terminal side right along our y-axis here, that was previously perhaps negative 90 degrees. Now it's going to be negative pi over 2 radians. Okay, over here we're going to have negative pi radians, and up here we'll have negative 3 pi over 2. Okay, now it can be helpful just because my angle I've been given to sketch has a denominator of 6. It can be helpful to look at these individual radian measures in terms of sixths, like rewriting them so that they also have a denominator of 6. That gives us maybe a better way of understanding exactly where this angle's terminal side should be. So for example, negative 2, if I were to represent that in terms of the denominator of 6, I would need to multiply by 6. So I'd get negative 12 pi over 6. Okay, I'm going to do that for the other 3 here. So negative pi over 2, if I were to represent that in terms of sixths instead, let's see, I would have, let's see, negative pi over 2, negative 3 pi over 6. Okay, negative pi would be negative 6, I guess I should write it there, negative 6 pi over 6. and negative 3 pi over 2. Okay, let's see. I've got to multiply both the top and the bottom by 3. That's going to be negative 9 pi over 6. So this might give me a slightly better idea of exactly where negative 5 pi over 6 goes. Of course, might as well go ahead and resketch our initial side of our angle. Now negative 5 pi over 6, well, it's more than negative 3 pi over 6, but it is less than negative 6 pi over 6. So again, I'm going to sketch, doesn't have to be super perfect, sketch that, this terminal side is perhaps a little bit closer to negative 6 pi over 6 than it is to negative 3 pi over 6. So let's sketch that directional, and we'll give it a little label, negative 5 pi over 6. So think about for a moment where exactly your reference angle is. I'm going to sketch mine in a second. Okay, hopefully we understand that it goes there. I want to maybe do it in purple actually. Here's our theta prime. So again, I like to ask myself, okay, how do I get negative 5 pi over 6 all the way to here, which for me is negative pi, or negative 6 pi over 6. How many more radians do I need to go, or do I need to like push that terminal side until it touches the x-axis? That's really what I like to think about. So let's see, that's going to be then 1 more 1/6 of pi. Notice this is negative 5 pi over 6, and this is negative 6 pi over 6, meaning between the two of them, there is 1 pi over 6 difference. I don't need to say it's negative 1 pi over 6 because a reference angle is always positive. So our theta prime here is going to just be equal to pi over 6. You could write that as 1 pi over 6 if you wanted to, or 1/6 pi, I guess. That's fine. This I would say is, kind of extra. We don't really need that number 1 in front of pi. But pi over 6 radians, that's how I would read my degree measure, or my radian measure. Now, the other way to perhaps think about that, and sort of back to maybe the formula idea, is that our theta prime is equal to, let's see, this is the one where I want to start with my angle measure, negative 5 pi over 6, and subtract pi. I'm not even going to write that as pi. I'm going to subtract, let's see, what was I trying to say? Subtract 6 pi over 6. Let's see, is that what I want to say? Subtract 6 pi over 6? Yeah, there we go. No, you know what, not making sense. Thanks for bearing with me here. Because we're talking about negative radians, I got to make sure that we're talking about negative pi here. So of course, that's going to then become, okay, my theta prime is equal to negative 5 pi over 6 plus 6 pi over 6, which means our theta prime is equal to pi over 6. So if you really prefer this, algebraic method where you sort of memorize the different formulas, great. If you prefer sort of just thinking about completing our line or completing the circle in other cases, that's great too. So let's look at a couple more examples real quickly here. Okay, 315 degrees. All right, it's degrees. We're talking about a positive measure. Here's my initial side. I know this is represented, represents 270 degrees, whereas this is 0 and 360 degrees. So 315 is again somewhere in between here. And I think it's actually halfway. Again, doesn't have to be perfect, mine's certainly not. There's my angle. Let's represent it's positive. It's going around counterclockwise. It's 315 degrees. And our reference angle, theta prime, is formed by that terminal side and the x-axis. So again, I am looking at this and thinking, okay, how much further, how many more degrees until I complete that full circle? So what do I need to add to 315 to get to 360? 315, there we go. And that's again where our formula comes from, 360 minus 315. Turns out here, theta prime will be equal to 45 degrees. All right. Okay, another example in radians. Again, we're going to move kind of quickly through this one. Pause as much as you need, of course. This time we're again looking at negative radians. Okay, so let's maybe add in again real quick. This is 0 radians and negative 2 pi radians. This would be negative pi over 2 radians, negative pi radians, and negative 3 pi over 2 radians. Okay, oh, but we've got negative 3 pi over 4. Okay, so if we put these kind of into fourths, we'll have actually negative 8 pi over 4, that's equivalent to negative 2 pi. Or we'll have negative, let's see, what am I doing? Negative 2 pi over 4, that's equivalent to negative pi over 2. Negative 4 pi over 4, equivalent to negative pi. And negative 6 pi over 4. Do comma. Okay, so again, that just gives me a better sense of exactly where my angle is going to end up here. There's our initial side right along the x-axis. And negative 3 pi over 4. Ooh, well, that's more than negative 2 pi over 4, but not quite as much as negative 4 pi over 4. And in fact, it's right in between the two again. So it's right about here. Again, just sketch. It's a negative angle measure, so we're going clockwise. Here we are, negative 3 pi over 4 radians. Okay, here's that reference angle, our theta prime. So how many more radians then would I essentially need to push this terminal side until it is right up against with my axis? So my, let's say, negative 3 pi over 4 plus what, that's supposed to be a theta prime, is equal to negative 4 pi over 4. That's an algebraic way of representing what's the difference between those two things, between my x-axis, negative 4 pi over 4, and my terminal side, negative 3 pi over 4. Theta prime always is positive, so we will say our answer is pi over 4, 1 pi over 4, 1/4 pi, perhaps, again. All those are perfectly fine. Okay, so you may be wondering, why on earth would we bother to identify all these different reference angles? And the reason is because it allows us to do some trig. So we can take trig functions, or we can talk about trig functions of what we're going to call general angles. Those are just going to be angles that we can plot in standard position with our initial and terminal sides. And oftentimes we're going to know that they go through some particular point. So that's what we're going to use here. P is going to be some point with an x and a y coordinate that we'll be able to say, okay, this terminal side of our angle goes through this point. So we'll be able to then figure out, using the Pythagorean theorem, all of the various measurements of a right triangle that will help us determine the 6 trig functions. Of course, the 6 being our sort of traditional 3, sine, cosine, and tangent, and then our reciprocal functions, cosecant, secant, and cotangent. Okay, now there's a lot going on here as far as formulas. Again, I am going to dive into an example. If you want to pause here and write all of this down very precisely, or come back perhaps and write all of this down very precisely, please feel free. But I think this makes the most sense if we look at what's really happening. So I'm going to look at our first example where we have the terminal side of some angle theta in standard position containing the point 8, -15. So the first thing is we're really going to need a set of axes. It doesn't have to be to scale. Like I'm not going to bother actually counting over 8 units and down 15. That's not what I'm going to bother with really. I'm just going to say, okay, this is roughly like 8. This will be roughly like -15. So my point will be roughly here. That's just about, and maybe I'll actually keep those little markings. This will be 8. This will be -15. Of course, along our x and y axes, respectively. All right. So I don't necessarily need to label that. That's just the point I'm given that my terminal side of theta goes through. So maybe I'll also plot my initial side and then my terminal side. I know the terminal side, let's see how well I can plot this, goes through here. Okay, good enough. Not the straightest of lines. You probably should use a straight edge. Now, I also don't necessarily know whether I'm talking about a negative angle measure or a positive angle measure. I don't know. It doesn't really matter. I don't really need to worry about necessarily drawing a directional and having a very precise graph of what theta looks like. This is enough. What I do want to know for sure, though, is what is my reference angle? Or where, I suppose, is my reference angle? My reference angle is going to be here. Now, we also then want to figure out essentially what on that previous page we called r, which is the distance between my point that's on the terminal side and the origin. This is the distance r. And what we're able to do then is actually say, okay, here's, yeah, this is the problem with it not being super precise. Let's get rid of that a little bit. This is one side of a right triangle. This is the other. Here's my right angle, where I know this horizontal distance because this is how far I had to go over for my x coordinate. So this distance is actually 8. And this distance is how far down I had to go to get to my y coordinate, oops, which is -15. So we can figure out what our length is here, what our distance is here, using that lovely Pythagorean theorem. So to find r, that's what I want to sort of start with here once I've got an idea of what theta looks like. Find r. Of course, that Pythagorean theorem, remember, is always given sort of generically as a squared plus b squared equals c squared. But a squared and b squared, those are legs of the triangle, not the hypotenuse. So that's 8 squared and 15 squared. And c, my hypotenuse, is actually r in my specific little triangle here. Okay, so we've got 64 plus 225, that's equal to r squared. Or let's see, if we add those together, that'll be 289. And you notice I tend to just like do that last step all at once. I combine that with taking the square root of both sides. So now we have the square root of 289 is equal to r. So r is going to be 17. Okay, so this is 17. Here's my reference angle, theta prime. Now the sine, cosine, and tangent of theta are all equal to the sine, cosine, and tangent, and all the reciprocal functions as well, of theta prime. So using this right triangle with theta prime as one of the angles inside of my triangle, I can go ahead and actually determine the exact values, are generally going to be fractions, of my general angle theta. So let's look at sine of theta. Sine, of course, if we're talking about SOHCAHTOA, remember you can write that all over everything. SOHCAHTOA is opposite over hypotenuse. Opposite my angle is going to be here. Hypotenuse is here. So that's going to be negative 15 over 17. Okay, let's get that out of the way. All right, so cosine, the ka of SOHCAHTOA, is adjacent over hypotenuse. So that's going to be positive 8 over 17. Tangent, TOA, opposite over adjacent, negative 15 over 8. Now when it comes to these reciprocal functions, like we've talked about before, we could go through the thought process of, okay, cosecant is the reciprocal of sine, so it's hypotenuse over opposite, or really we could just take sine, whatever we had for sine of theta, and flip it over. Take the reciprocal of that value. So we'll say this is negative 17 over 15. Okay, same for the others. I'm just going to pick new colors. 17 over 8. And let's do red. Negative 8 over 15. Okay, so those are the 6 exact trig functions of theta. Okay, and that's the beauty of reference angles. It allows us to take literally any angle if we know that the terminal side goes through some particular point. We're going to be able to then determine this r value, which essentially represents the distance, again, between our 0, 0, between our origin and said point, and that will get us to all 6 of our trig values. Okay, so there are a couple extra examples that I want you to look at, and when we get back together, we will talk about them. So here's actually just this one last example where the terminal side goes through the point in standard position, negative 3, 4. So I'll go ahead and work on that. We're again identifying the 6 trig functions of theta using the reference angle theta prime. Okay, when you're all ready, go ahead and rejoin or go back into Teams and we will talk about it. Okay, have a great day, have fun.